Hello guys, welcome to the DMS online school. In today's video I'm going to revise with you science paper 1 2020. It's actually a revision guys that I'm doing. I'm re-uploading this video on the basis that the first one which I did had a lot of noise. The music that I added to it had a lot of noise and most of you complained, so I decided to re-upload this video without the music. Alright, so this is examination for school certificate ordinary level science paper 1 2020. All right, so without wasting much of your time, let's go into the revision. All right, so this is question number 1 guys, which reads how many significant figures are in 2.0800. So as you know, for you to be able to answer this question, unless you know the rules that determine significant figures. So here are the rules that I'm going to revise with you. So rule number 1 says digits that are not zeros are significant. So digits that are not zeros are significant. Digits that are not zeros are significant. E.g., if we have 342, 342, all these digits are significant, and this 342, we can say that there are 3 significant figures. Also, number 2, zeros between non-zero digits are significant. So, e.g., we have 2004. 2004. So we have 2 zeros that are in between 2 and 4. So these 2 zeros are significant. So in this number 2004, there are 4 significant figures. All right. Another one is here where we are saying zeros at the end of a digit with a decimal point are significant. So zeros at the end of a digit with a decimal point are significant. Let's say we have 58.0. So in this one, this 0 is significant because it comes after a point. So in 58.0, we can say that it has 3 significant figures, 1, 2, 3. Also in 73.30, this 0 here, again, it is significant because it comes after a number in a decimal point, so it is significant. So we can say in 73.30 we have 1, 2, 3, 4 significant figures. Another rule says that zeros before non-zero digits in a decimal number are not significant. So if you have zeros here that come before a non-zero digit in a decimal number, these zeros are not significant. This one and this one, they are not significant. So in this number 0.0453, there are only 3 significant figures. So we can say in this number there are 3 significant figures. Also another rule says zeros after non-zero digits in whole numbers are not significant. So in 42,700 here, so we have these zeros that are coming after non-zero digits in this whole number here, which does not have a decimal point. So these 2 zeros are not significant. So we can say in 42,700 there are only 3 significant figures. So according to this question, how many significant figures are in 2.0800? So since in this number here we have it is a decimal point, and then we are saying these zeros will be significant. So there are how many significant figures now here altogether? 1, 2, 3, 4, 5. So our answer is D, guys. So question number 2 says which of the following contains base quantities or base physical quantities only? So which of the following contains base physical quantities only? So you need to understand what are base quantities, guys. So we are saying base quantities, what are they? We are saying these are the fundamental quantities that cannot be expressed in terms of other quantities. They have only 1 SI units. Yeah, so we have quantities which we call the base physical quantities, and this one cannot be expressed in terms of other quantities or cannot be described by other quantities. So they only have, again, single SI units. So we are saying these are length, which is measured in meters, mass in kilogram, and the time in seconds. So these are the fundamental three base physical quantities. So when we check with our question which says which of the following contains base physical quantities only, you'll see that here we have length in kilometers, mass in tons. Tons is not a base physical quantity. Here B, we have length in meters, mass in tons. It is not a base quantity, tons here. Then we have length in kilometers, mass in kilogram. That is not true. Then here length in meters, mass in kilograms. This suits very well. All right, so our answer here now becomes D. All right, so now let's move to another question. So this is question number 3. Question number 3 reads, the following diagrams show steps that a learner carried out in order to determine the volume of a wooden cork. So the following diagrams show steps that a learner carried out in order to determine the volume of a wooden clock. Yeah, so these are the steps, step 1, step 2, step 3. So in step 1, when it has no wooden, there's a wooden cork, and then there's also a glass bulb here. See here, all right. So here, without anything here, we must read the volume, right? So you need to know how to read this volume. If you check, if this is 20, then here there's 40, then here 60, then in between here it is 10, 10. If you start from here 0, then it should be 10, 20, 30, 40, then 50. So the volume here, without anything, it is at 50 cubic decimeters. All right. Then after now, step 2, Elena put a glass bulb there. We have seen that the volume went to 60, right? Yeah, so it went to 60. So now let's see the volume of this glass bulb alone, which moved it from 50 to 60, which is 10. So you can say actually, we are saying final volume after a dipping glass bulb is 60. So we are saying then the volume of the bulb will be 60 minus 50, which will be 10 cubic centimeters as the volume of a glass bulb. Yeah. So here again, you see on step number 3 here, the learner had to put this wooden cork. So there's a wooden cork and then added another glass bulb here. So now there are 2 glass bulb here and this wooden cork, and then the volume now has gone to 100. All right, so the question says which one is the volume of the wooden clock? So they want to know this volume of the wooden cork here. So simple, right? So you just need to carry out these steps. So you see that our final volume after dipping to glass bulb, then wooden block is actually wooden cork is actually 100 cubic centimeters. All right, so now for us to know the volume of this guy, we need to use this one. So here the water is at 100, then you subtract 50. So you remove 50 first, which was the original volume. So you need to know what went here. All right, so from here to there. So you remove first the original volume for you to know this one, which you are saying 100 minus 50 original volume, then also minus open brackets 2 times 10. So these each one of them is 10. Now there are 2. So now which will be actually 20. So you say 100 minus 50 cubic decimeter minus 20, then you get your answer as 30 cubic centimeters. So your answer is A, which will be the volume of this guy here. Right, so let's move to another question here, which is question 4. So question number 4 reads, which of the following diagrams show an accelerating car? So we have these diagrams A, B, C, D. Now they want us to find out which one is the one showing an accelerating car. Yeah, so before you answer these questions, there are few theories that you need to know. So we have this theory number 1 here on a distance time graph. Before we look at the theory. So these are distance time graph here, vertical axis distance here, horizontal axis time here, also distance here, time here, distance here, time here, time here, distance. So now you need to understand what this graph represents on a distance time graph. So what you should understand is this: if you have a graph like this one, where now you have distance as usual and the time here, it is a distance time graph, this one. But if you have a straight line like this one here, like A, B, C, D, such a graph like this one, we are saying AB here, AB represents actually constant increase in speed. So if a line is straight on a graph like it's going like this, it is a steep slope, an upward slope like this one, then it means like that it is actually from A to B, it is actually increasing constant speed. Then BC, where the line is horizontal and going in the direction of the time like this, meaning that it represents a stationary object, because meaning in this way distance is not increasing, but time this way is increasing, so time is moving. So when time is moving, distance is not moving, it means the object is stationary. Then CD here, CD then represents decrease in speed. So this is constant decrease in speed for a sloping downward slope, or for a downward slope. So this one does not match any of these here. All right, so there's no acceleration in this one. So distance time graph does not show actually. When a line is constant like this, it doesn't show acceleration, it's actually constant in speed. All right, so let's look at another one here. So we have other situation here, distance time graph. We have this one, distance here, time. So when you have a curved graph facing upward like that, then it means acceleration. Then when you have a curved graph facing towards time, when it is facing towards distance, then it is accelerating. When it is facing towards time, distance time graph, then the graph is curving facing towards time, then it is decelerating or retardation. So when we look at this one, which one matches our graph here, where we're saying which of the following diagram show an accelerating car? So you see it should be B, because it is facing towards the distance. So let's move to another question. So this is question number 5, which reads, the diagram below shows a light bar PR pivoted at P, balanced by a 4 Newton weight and the force F. So yeah, we have a light bar. This is what they are calling a light bar, which is actually balanced by a 4 Newton weight, and then there's also a force here, Newton balance here. Then the question says, what is the reading on the Newton balance? So this Newton balance, which is lifting this part here, actually here there's a pivot somewhere here, so they're lifting this one here. Then they want to know what Newton balance will show here, the reading. So this is a moment question coming from moments. So if you want to revise on moments, I have a lesson, and then you can pay something, then I'll be able to add you to the group where the lessons are occurring on moments, so that you understand very well explained lessons. All right, so here now you understand this is a pivot, then there's this force which is facing upwards, meaning this force tries to lift this thing upwards. Then there is this weight here actually, so this weight is tied here, so you know weight always acts towards the earth, so this weight again is pushing it downward. Now we are told that it balanced, so if it is balanced, it means the force taking it this way and the one taking it down are equal. So that means this light bar is in equilibrium. So using the principle of moment, we'll be able to find this force upward here. So we are going to say that let's call this force, according to moments, we can say force 1, which is the one carrying it this way downward, times distance 1. So this distance 1 is the distance of this force carrying it downward from the pivot. So you consider from the pivot. So we are calling this force 1, and then we are calling which one again are we calling? This one we are calling distance 1. Yeah, so this one is distance 1. Then this one is so the distance 1. So if this is force 1, which is 4 Newton weight, then where it is hung from the pivot, then this is its distance. So it is at 30 centimeters. Then we are saying let's call this force here, which is force 2. All right, then this force 2, its distance from the pivot now is actually this distance here and this distance when you add them. All right, so meaning that when you multiply this force times its distance from the pivot is also equal to this force here times its distance from the pivot. That's why this thing now stands in equilibrium or state of balance. So now let's just begin with this side where we want to know force 2, which is the weight that is going to be read by the Newton meter. So we'll restart like this. So I just swapped this. So now we are going to start substituting here, guys. So now what we are going to do here, we'll say F, which we don't know, F2 times 50. So this is 50 distance, D2 is 50, which means 20 plus what? 30. So from here to here it is 50. So that is the distance here. So 30, then the 20 plus 30, 50 is equal to, then this first one, it is actually 20 Newton, then times, then D is actually from here to here, which is 30. Then when you multiply F2 times 50 centimeters, you get actually 50 centimeters. F2 equals, then this times this, it will give you 140 Newton centimeters. So 4 times 30, 120. Then you write N centimeters afterwards. Then you want to know what F2 is, so you divide by 50. Then here you divide by also 50. So why are we dividing? It's easy to remain with F2. So since between these 50 centimeters and F2, in between here there's multiplication, then if you want to get rid of this, the rule is that when there's multiplication, to get rid of the quantity you don't want, then you need to divide. That's the rule. So if you are dividing by 50 on this side, then according to equation, you also must do the same on the other side, so that the equal sign means the same. So 50, 50, it means the same. So then you cancel 50, you cancel 50. Then what you are going now to have is to divide this into there. So this also unit and that one will cancel. Then you remain with F2 is going to be equal to, when you divide 50 into 120, it will be 2.4. Then in Newton will come here. So your answer will be B. All right. So let's see 6. So 6 is here, guys. We are saying a car is traveling on a level road. Suddenly the driver of the car sees a cow crossing the road and decides to apply brakes. What are the energy changes as the car slows down? All right, so the point is here, they are saying a car is traveling on a level road, right? Then they're saying that what we should know is that a car traveling on the level road has what? Kinetic energy. So if a car is traveling, then it has kinetic energy. All right. Then they're saying suddenly the driver of the car sees a cow crossing the road and decides to apply brakes. So here the driver now decides to apply brakes. So here we are saying that when brakes are applied on a moving car, tires stop rotating. This causes friction between tires and the road. And then we are saying what are the energy changes as the car slows down? So we are saying that the friction force produces sound, and heat energy as the car slows down. So this is the point here. So if you have ever heard before, when a car emerges or brakes or applies brakes in an emergency situation, you can even hear sound, even in the movies, even in real life. I think those situations happen. So because there is friction force between which friction force produces sound and heat energy. So even when you rub your hands like this, because you produce friction, right? So you feel some heat there. So these are the energy changes. So the question is saying, what are the energy changes as the car slows down? So A, chemical to kinetic energy and the sound. So we have chemical as the car is slowing down. So what are the energy changes as the car slows down? No, the car was moving, didn't have chemical energy. So they're saying it will be chemical energy to kinetic energy and to sound, no. Then they're saying heat to kinetic energy and sound, no. Kinetic energy to chemical and sound, no. Kinetic energy to heat and sound. So this is what happens. What are the energy changes as the car slows down? So it will be from kinetic, because the car is traveling on the road, so it will have kinetic. Then here we said when brakes are applied on a moving car, tires stop rotating. So this causes friction between the tires and the road. So there will be friction, and that friction force produces what? Sound. So we are saying there will be sound, and heat, so there will be sound. So kinetic to heat and this sound. So this is our answer. So let's move to another question, which is 7. 7 says the graph below shows a cooling curve of a gaseous substance. So there is a cooling curve of a gaseous substance, here energy, here time. Then the question says, in which states of matter will the substance be between point F and G? Yeah, so where is point F and G? F, G, F, G. So it's a substance being cooled. This substance being cooled is in a gaseous state. So when it is being cooled, you expect it to change from gas to liquid, right? And if they continue cooling it, then it should change from liquid to solid. That is all. Yeah. So now what you should understand here is that we can cut this into parts. We cut this part, we cut this part. So you notice here what I'm writing here. So I've cut this part here, one section. So what I'm saying here is that from E to F. So from E to F, the substance is in a gaseous state. So as it is being cooled, so the graph now faces downward, meaning energy starts decreasing of this substance. Now during this E to F, we are saying the substance is in gaseous state and the line slopes downwards because energy is lost as the substance is cooled. Yeah, that's the fact here. So here we have only gaseous only. That's how it is. All right. So then next we draw another line at this time where the graph again is dropping. Then again we are explaining here that from F to G the line is flat. Yeah, F to G the line is flat or horizontal. This means energy is constant. Yeah, so where the line is constant like this, then energy is constant. Actually energy is the same. So constant as the substance is cooled, here the substance is changing from the gaseous state to the liquid state. Yeah, on this part why it is constant is because now the energy which is applied as this substance is cooled, as this substance is cooled, the energy doesn't drop continuously. Why? Because now at this point the substance is changing from gas to liquid, and as it is changing from gas to liquid, it produces some of the energy by collision. Those particles, when they are colliding, they also produce some energy, and that energy is what maintains the temperature to be the same. All right, so that is actually the cause of this constant in temperature. All right, then when we check now at another point here, so we are saying from here there's gas to liquid, there's change here. So we have here gas and liquid because the gas is now changing from gas to liquid. That's why here it will drop. So when we draw here, we are saying that from G to H here, the substance is in liquid, here. All right, so it is in liquid because now after it has changed completely from gas to liquid here, again the temperature drops as it is being cooled. So we are saying, and the line slopes downwards because the liquid particles loses energy as it is cooled. All right, so now we can also draw another one here. Then we are saying from H to G here, from H to I, so from H to I the line is flat. Here the substance is changing from liquid to solid. So liquid to solid, it stays flat because particles in liquid produce energy as they slow down to take the solid state. Yeah, so here now it is changing from liquid to solid. So here we have liquid and the solid state. All right, so when they say in which states of matter will the substance be between point F and G, then it will be gas and liquid, which means our answer is C. All right, so let's go to question 8. So question 8 says the following diagram shows a water wave. Yeah, this is a water wave. So we have this one vertical axis, horizontal axis. We have from the crest to the trough, we have been told the distance is actually 8.0 centimeters. Then we have been told from the equilibrium of this trough to another equilibrium, then the distance is actually 5.0 centimeters. Then they're saying which law gives the correct values for the wave amplitude and the wavelength. So we have this row here. So on this row we have here amplitude in centimeter, wavelength in centimeter also. So the question is saying which of these rows gives us the correct values for the wave amplitude and the wavelength. So for you to answer this question, you must understand what the amplitude first is. So the amplitude is the maximum displacement of a wave from its equilibrium. The equilibrium is the rest position. For instance, on the water, when water has got no waves, it is just calm, then it is at equilibrium or at rest. Now when you throw a stone or an object in water, waves are produced. Then waves are produced. So now waves start rising from the equilibrium to up and down. So the equilibrium is the rest position, and this line represents the equilibrium. So now the amplitude are these, the top of the crest. So these crests or the troughs, these are actually the distance from the equilibrium to the top of the crest, like this one here. From here to there, this is actually the amplitude, all right? So this is the amplitude from the equilibrium to the top of the crest, or from the equilibrium to the trough of the crest. I mean to the trough of the wave, yeah. So now, so this one is the amplitude from here to here. All right, so amplitude now, when we come here, we have been told now from here to here it is 8. So meaning from here to here we divide 8, which means we'll get what? 4. So amplitude should be 4. So 4 here, 8 wrong. So between A and B, our answer lies here. Now wavelength. Again, wavelength, this is the definition. Wavelength is the distance between successive crests. So successive crest meaning crest following each other. So between this crest and this crest, the distance here is what we call the wavelength. Here we are saying, or 2 points, excuse me, on the wave that are in phase. So 2 points on a wave that are in phase are similar points, in short, similar points. So it can be a distance from here to here. Here when it is rising at this point, and at this point when it is rising. These are similar points. So also distance between 2 points on the wave that are in phase, in short, just similar points. These words that are just there to confuse. So wavelength, hence we are saying it is this distance from crest to crest. All right, so that is the wavelength, this one. Then also from here, I've said from here to here, so that is wavelength as well. Now notice one thing here. We have been told from here to here it is what? 5.0. So notice from here to here it's the same as from here to here. Now if we want to say from here now to here, what is it going to be? So from here to here it is 5. Also from here to here it is also 5. So if you add 5 plus 5, it is going to be what? 10. All right, so it is going to be 10. So meaning that wavelength is going to be 10, right? So 10 wavelength here, guys. So our answer is going to be A. So let's answer 9 here. So 9 says the diagram below shows a learner in front of a loudspeaker that produces sound. All right, so the diagram below shows a learner in front of a loudspeaker that produces sound. So this is the learner is in front of this loud speaker producing sound. This is the classroom wall here. Then they're saying which of the following diagrams best shows how the gaseous air molecules between the learner and the loudspeaker will move. So there will be gaseous molecules here. When the sound is produced here, it is this thing speaker is moves forward and backward, so it pushes air molecules here. So these air molecules here, how do they move here? So what you must remember is that sound is a longitudinal wave. All right, so Sound waves causes particles of the medium to vibrate parallel to the direction of travel of the wave. So they will go like this, because why? Sound is a longitudinal wave. So in a sound, the direction of particles of the media are parallel to the direction of travel of the wave, like this here. So direction of the sound will be going like that from here to the ear. Now particles will be moving like this also. That's how they'll be vibrating. Yeah, so now this is the situation which I gave. This is how they'll be vibrating. As they're moving, they'll be vibrating like that. All right, so this particle here, see, it goes, it comes back, it goes, it comes back. That way sound is going, but particles, they don't move themselves. So you see, they don't move. All right, so the answer here is what? Is A, which shows how particles will be going like this, like I've demonstrated here. So it is going like that, like that. So the answer is A. So guys, I just want to inform you that we are also going to do revision in science. Past paper 20, we'll do 2014, 2015, 2016, 2017, and also to some extent 2018 science papers, physics, which is science paper 1, chemistry, which is science paper 2. So if you are interested to join, the number is on the screen there, 0977 9241 75. Just give me a WhatsApp message, and then the price is very actually affordable. Physics and chemistry, it is 60 kwacha. Then biology, which I'm already revising, also it is at 30 kwacha. Yeah, I want everyone to revise, because I know when you revise, you are going to make it so that next year you continue with your program which you are doing. All right, so let's move to another question. So question number 10 says, a girl of height 1.2 meters stands 4.0 meters in front of a plane mirror as shown in the following diagram. So we have a girl here whose height is 1.5.2 meters, that is her height, and they're saying stands 4.0 meters in front of a plane mirror. So there's a mirror here, and then she stands from the mirror 4.0 meters. All right, then the question says, how far is the girl away from her image? Yeah, so they want now you to know the image of the girl. Now remember, when you look at yourself in a mirror, the mirror that you look at when you are dressing is actually a plane mirror. All right, so how do you see yourself when you look in the mirror? You see yourself as if you see your image in the mirror, as if yourself, the distance between yourself and the mirror, and then that image of yours from the mirror again, it seems it is the same. If you have a mirror right now, go and check yourself. So it means now these guys are saying, how far is the girl away from her image? So her image, this girl, will be somewhere here. So the image is far behind the mirror as the object is in front of the mirror. So you'll find that this is her image. And if herself she's 4.0 meters from the image, then also the mirror, also the image is also 4 meters away from the mirror, and also the image should be 1.2 meters as well. So now the question, as they say, how far is the girl away from the mirror? So these points which I'm bringing out here, they're actually coming from characteristics of images. All right, so characteristics of images. So these are characteristics of images here formed on a plane mirror. So according to characteristics of images formed on a plane mirror, we say that the image is always upright, like this one. The image must be upright as the object, and it must be virtual. So it is a virtual, this image, meaning that cannot be captured on the screen. So this image does not appear on a screen, then it is literally or laterally inverted, meaning to be laterally inverted, the left side of the object on the mirror, it actually appears as if it is the right side. That's what it means. So which means left and right are swapped around. Then same as the object, same size as the object. So if the object is 1.2 meters, even the image must be 1.2 meters. Then they're saying the image is as far behind the mirror as the object is in front. So this image is the same as far behind the mirror as the object is in front of the mirror. Yeah. So these are characteristics, guys. So the distance then will be the distance of the girl away from her image will be distance of body plus distance of image, so which will be equal to 4 plus 4, which will be equal to 8. So here it will be actually 8, this 4 plus this 4 here. All right, so let's answer again this question here. So this question says a line JK drawn on a piece of plain paper on which a glass block is placed was viewed through the top, and its image was located using a pin as shown in the following diagram. So we have a line JK which has been drawn on a plain paper, then on which a glass block is placed. So this is a glass block, it is placed here and viewed through the top. So this is the eye viewing through the top to see this line, and its image was located using a pin. So this guy, as he was viewing this image somewhere, it was located using a pin as shown. So the guy, when he was looking through this glass block, saw this line as if it was here where he put the locating pin. So this is where the image appeared to be of this line. So this is the glass block. Yeah. So then they're saying if KL is equal to 1.8 centimeters. So they're saying KL, where is from K to L, it is actually 1.8 centimeters, and again from KM it is 4.8 centimeters. Then they are saying what is the refractive index of the glass? What is the refractive index of the glass? All right, so simple. So refractive index is always given by the formula where we say real depth divided by apparent depth. All right, so now let's understand very well here. So what you should know is that from here to here, this distance from here to here, we call it real depth. All right, so this is real depth here. All right, then another thing to know is that it is actually 4.8 centimeters. Then what you should know from here to here, from where this object is seen, the image of this line is seen L here, where the pin is, to the eye. This one is called the apparent length, all right, or depth. So this line from the eye to where the actual line is, we call it real depth, and we have been told Km is equal to 4.8. That's why I've said 4.8. Now here we have been told KL is 1.8. From here to here it's 1.8, but the apparent depth is from here to here. All right, so now from here to here I'm saying 1.8 centimeters. Now if we want to find the real depth, it is from here to here, this real depth from here to here divided by from here to here. That's what is used to find the refractive index. So we are going to say refractive index is equal to real depth over apparent depth here. So now which will be equal to, so real depth is 4.8, then divided by apparent depth from here to here. So you are going to say 4.8 minus 1.8, which is going to be 3. So 3 centimeters from here. So you divide, which will give you, first you cancel those. When you divide, you get what? 1.6. So your answer is C. Then here we are told that in A12, which of the following materials would be most suitable for constructing the core of an electromagnet? Which of the following materials would be suitable or be most suitable for constructing the core of an electromagnet? So the core of an electromagnet is actually a substance upon which the coil is wound. So what the situation they're talking about is like this one here. So this one is a coil. Then in the coil here, when you put a substance here, like something like here, and then current starts flowing here, then this substance which you put here becomes a magnet. There are two substances that we put here. Either we put in iron or steel, either iron or steel, something which is magnetic. So when you put something here and the current passes like that, then this whole thing becomes an electromagnet. All right, so this one now becomes an electromagnet. All right, so then we are saying that iron, so according to the question, which of the following materials would be most suitable for constructing the core of an electromagnet? So here we are saying iron, because it is easy to magnetize and demagnetize. Yeah, this is a nice theory, guys. So when we are making magnets, we have two types of magnets. We have what we call temporal magnet and permanent magnets. So materials that are hard magnetic materials like steel cannot be used to make an electromagnet, because once steel is placed here, then current flows, then this one will become a permanent magnet, because steel is a hard magnetic material. But if we use iron, we put it here, iron is a soft magnetic material, meaning it is easy to magnetize and easy to demagnetize. So it is the one which is suitable to be placed here to make an electromagnet. So the answer is C. So carbon is not a magnetic material, copper is not a magnetic material, so these one are not answers. So let's move to 13. So question 13 says two uncharged metal spheres Q and P are placed on insulating stands and are suspended with the negatively charged polythene strip and are separated, while the negatively charged polythene strip is held near Q as shown in the diagram. So here we have uncharged metal spheres. We have Q and then P, uncharged metal spheres, and they are put on what? Insulating stand. These are insulating stands. So these are metal spheres. Then we are told that negatively charged polythene strip is held near Q. So this one is negative charge held near Q. Then they are saying what would be the charges on Q and P. Yeah, so here there will be actually induced charges. When you bring a charged object closer to an uncharged object, what happens is that since this one has negative, so negative and the positive here. So now before I say that, so this is uncharged, it doesn't have charges. So what it means if it doesn't have charges is that it has charges, even if they are not shown, it has. It just means that the number of positive charge and the negative charge, they are equal. That's why we can say that it is uncharged. These are uncharged because the number of positive charge and negative charge, they are equal. So here there's also positive and negative equally here, but when you bring this one closer, since it is negative, it is going to repel all the negative charges which may be here and only leave the positive charge. So these negative charge which are here, they will be repelled by negative, because negative repel, so they will come here. So here you have one positive and the negative will be this side. So now that's how it is going to be. So when they say what would be the charges on Q and P, so you see on Q it is what? Positive, right? Then on P it is negative, so positive, negative. So the answer is B. Yeah, so let's move to question 14. Question 14 says the following diagram shows a network of 3 resistors R1, R2, and R3 connected to a battery. Then voltmeters V1, V2, and V3 are connected to R1, R2, and R3 respectively. Yeah, so this is what they are saying, that we have a network of 3 resistors, R1, R2, R3. They are all connected to a battery here. Then also we have voltmeters V1, V2, and V3 connected to what? To resistors as shown. Then here we are told which of the following expressions show the potential difference supplied by the battery. So potential difference is just voltage which is coming from here. So it is simple, this situation, guys. So they need the formula which will show the potential difference coming from what? The battery. So there are a few points to note here. Point number 1 is that voltage is the same in parallel. So like here, resistor 2 and resistor 3 are in parallel. So this voltage that will be read on a V2 and the one that will be read on a V3, they'll be the same. Why? Because these two are in parallel. Then that's why we're saying voltage is the same in parallel, and R2 and R3 have the same voltage since they are in parallel. Then another point to note is this one, where we are saying voltage is not the same in series. So this resistor and these two, they are now in series. So voltage will not be the same. What will be read on this voltmeter 1 and what is read on this V2 and V3, they will be different because voltage is not the same in series. So we are saying voltage is not the same in series. This means that voltage for R1 is different to voltage for R2 and R3. So they will have different voltages. So now if you want to know the voltage coming from here, it is either you say that you are saying so potential difference should be given by the voltage which is read by this one plus either this one or this is V plus V2 here, because this one and this one, they're just the same, or I said or V1 plus V3. So either you get this one plus this one or this one plus this one, because they will be just the same. This one, if it reads 2, even this one will read 2 because they are in parallel. So then the formula will be this one or this one. So the answer is A. So 15 says an electric kettle is rated 230 volts, 3000 watts. What is the suitable fuse to use on this kettle? So an electric kettle is rated 230 volts, 3000 watts. What is the suitable fuse to use on this kettle? So a fuse actually allows current to flow through it. So when they are saying the fuse, then they want current that is suitable for such ratings. So we know that for us to know current, we should see what we are provided. We are given 230 and also 3000. So 230 is voltage, 3000 is actually power. So they are asking us the fuse, meaning current. So we have power, voltage, power, current. So this is the formula which connects the three, which is the power is equal to current times voltage. Now we want voltage, so I mean current, so use this formula here, simple, to help you understand this situation here. So here we have power, current, voltage. So this is a triangle which helps us to make each of these guys the subject of the formula. So if you want current, then you get power divided by voltage. If you want voltage, power divided by current. If you want power, current times voltage. Now we want current, so power divided by voltage. So have current is equal to power divided by voltage. So power is what? So current is equal to power is 3000 divided by voltage is 230. So if you divide, you get 13. So when you check here, 13 is not there. So according to power rating and the fuse use, so you don't use the fuse that is exactly exactly with the current that flows through it. So the fuse that you must use must be quite larger than the current. So these 230 and 300 will need the current of this. Now the fuse should be slightly higher than this, so which is 15, which is slightly higher as the answer. So let's move to question number 16. So question number 16 says below are three statements on electromagnetism. So we have one, an electromagnet consists of a coil of wire wound on a soft iron core. Then two, they're saying the strength of the magnetic field produced by an electromagnet increases if the strength of the current and or number of turns of wire is increased. Then 3, in the diagram below, when the switch is closed, the gap R increases. Then which of the above statements is true? So let's see. Statement number 1 says an electromagnet consists of a coil of wire wound on a soft iron core. That is true. We even saw the other question that we answered. So statement number 1 is correct. Then statement number 2, the strength of the magnetic field produced by an electromagnet increases if the strength of the current or number of turns of wire is increased. So statement number 2 is also correct. The strength of the magnetic field produced by an electromagnet increases if the strength of the current or number of turns of the wire is increased. True. So this is true so far. Then 3, they're saying in the diagram below, when the switch is closed, the gap R increases. So the gap R increases when this switch is closed. So then we need to understand very well. So here the situation is like this. Let me just show you what is happening here. So on this one, when the switch is closed, so current will flow like this. That's how it is going to flow. Then it will come like this again. So using right hand grip, you find that when current is going like this, then this one becomes north. Then this one becomes south. Now this is R, right? So let me just remove this one. So this, I'm saying, becomes north. This one south. Now this one is a magnet, south. So you must know that the south and north will attract. So if they will attract, this gap will decrease. Now here they're telling you to say in the diagram below, when the switch is closed, the gap R increases, which is not true. So this statement 3 is wrong. So only 1 and 2 are correct. So the answer is A. So let's move to question number 17, which says the diagram below shows a filament lamp rated 6.0 volt connected to the output of a transformer. So we have a filament here rated what? 6.0 volt. So this one is 6.0 volt and it connected to the output of a transformer. So this is a transformer here. So we have a transformer. This coil here is the input, then this other one is the output. That's where it is connected. Then they're saying what happens to the lamp when the current is switched on. So when the current is switched on, you know that this transformer has 300 turns, then the voltage passing here is actually 240. Then here we know there are 20 turns here. Then this one is rated 6 volts. So 20 turns, but we don't know the voltage that will come here. So they are saying what happens to the lamp when the circuit is switched on. A, lights dimly. So this one lights dimly, the lamp lights dimly. Then B, does not light at all, it will not light. Then C, lights at normal brightness. Then D, lights up brightly and then blows off. So for us to answer this question, it's a tricky question that you need to see that for you to be able to answer this question, unless you understand it, you calculate one variable here. In a transformer, we have what we call voltage in the secondary here over voltage in the primary. So this one should be the secondary and then the primary. Primary, secondary. So voltage in the primary, it's the input of the transformer, then the secondary is the output. So voltage here, which is this one is the secondary, voltage in the secondary here divided by voltage in the primary here must be equal to a number of turns in the secondary here, number of turns which are here divided by number of turns which are in the primary. So now we need to know voltage in the secondary here. So we'll say voltage in the secondary, making this the subject of the formula, it will be equal to voltage in the primary times number of turns in the secondary divided by number of turns there. So you must understand how to make Vs the subject of the formula. I did a video already on my channel on how to change the subject of the formula, and I'm sure you have even watched many videos on YouTube on this channel that teach mathematics. So this one should be a no-brainer for you. So now from there, now you say Vs now is equal to Vp, voltage of the primary is 240, then Ns, which is number of turns in the secondary here, which is 20. So it will be 240 times 20 divided by number of turns in the primary, which is 300. So you say voltage is going to be 16. So here, when here you have 240 with the turns 300, here if you have 20 turns, then the voltage that it will produce this transformer will be 16. Now this lamp connected here, it only uses what? 6 volts. So meaning here there's too much voltage which is coming out. So that's why it will light up. It will lights up brightly because it has more 16, and then it blows off. Yeah, to blow off because 16 is too much to handle. So that will be the answer. Then let's go to question 18. So question 18 says, which component used in electronic circuits allows current to flow through in one direction? So which components used in electronics or electronic circuit allows current to flow through in one direction only. So on a diode here, so a diode is the one that allows current to flow in one direction only. All right, so 19 says an atom of uranium 3-235 has 92 electrons. Yeah, how many protons are there in one atom of uranium? So you remember, a number of electrons and number of protons, they are equal. So we are saying in a neutral atom, number of electrons equals the number of protons, or atomic number. So if there are 92 electrons, how many protons? Also 92. So the answer is A. All right, since there are 92 electrons in uranium 235, this means there are also 92 protons. So 20, a radioactive material gives a count rate of 8,000 counts per minute. After 20 days, it gives a count rate of 50 counts per minute. So what is the half-life of the material? Yeah, so this one is an interesting question. So you need to understand what half-life is. So half-life is the time taken for the amount of a radioactive substance to decay by half. So half-life is just time taken. So I always try to explain it to people that this concept of half-life is so simple, but people don't agree. So half-life is the time taken for the amount of a radioactive substance to decay to half. Now, let me put it in a simple way. I don't know if in the previous video this is what I said, but let me say it in this way. Let's say you are popping up popcorns, guys. So maybe you have 10 popcorns. So the half of 10 is what? 5. So let's say you start popping, you have a stopwatch, and you want to know the time it will take for half of the popcorns to have popped out. So if you have a stopwatch, you start popping, you start the watch as you start frying the popcorns. Then the stopwatch will be counting as you are frying. So popcorns, they'll start popping. Now imagine these popcorns if they were popping in order, one after the other. One pops out, you count 1, another one pops out 2, another one 3, another one 4, another one 5. When the 5th one pops, you stop the watch. Then you look at that time. That time, then it will be called the half-life, meaning the time taken for half amount of the popcorns to have popped out. That's how it is. So simple. So here when they say a radioactive material gives a count rate of 8,000 counts per minute, meaning when 1 minute passes, maybe gigamolar tube or counter should produce 8,000 counts, which are sometimes beeps, because a gigamolar produces some sound when it is actually measuring radiation. So in 1 minute, maybe it has produced my beeps, which are 8,000. So meaning every minute, that's what it should be producing. Now, since this one is a radioactive substance, these count rates, they always decrease with time, because the substance is breaking, converting itself into another substance. Yeah, that's what actually happens. So meaning, they're saying after 20 days, it gives a count rate of 500 counts per minute. So it was giving initially 80,000 counts per minute. Now after 20 days, now it is only giving what? 500 counts per minute. So what is the half-life of the material? So meaning, for you to be able to find half-life, you should continue halving this one. You halve it, you halve it, you halve it, you halve it. So at the beginning, you have 8,000 count. All right, 8,000 what? Count per minute. Then if you halve it, you should halve it until you reach what? 500. If you halve it, what do you get? 4,000. If you have 4,000, what do you get? You get 2,000. If you have 2,000, what do you get? 1,000. If you have 1,000, what do you get? 500. Now you need to know now how much it has taken, time now which it has taken. They have told you that they have said after 20 days it gives count rate. So from here, from 8,000 to 500, the total time taken is actually what? 20 days. Now if from here to here it is 20 days, how much can it take for half-life? Since half-life is the time taken for the amount of a radioactive substance to decay by half. For instance, the time that it can take for this one to decay from 8,000 to 4,000, that the time it will take here, 8,000 to 4,000, because it will be half at 4,000 here. That time it will take, it will be half-life. But however, from here to here it has taken 20. So how many has it halved? 1, 2, 3, 4. So since if it has halved 4 times in 20 days, now how much from here to here? So you just say 20 for all 4 of them. How about 1? You say 20 divided by 4, which will give you 5 days. So we are done with the section A. Let's go to section B. As usual, guys, I'm trying to remind you that their revision is coming in July. We'll do vigorous revisions up to the time of writing exams. I said the charges are only 60 kwacha science. So if you want to pass seriously and forget about rewriting, then pay the 60 kwacha. And then let's revise. Let me help you pass so that you move to another level of your life. All right. So now let's move to section B. So this is section B here. So in section B here, you write answers actually in the spaces provided. So B1 says figure B1.1 below shows a simple pendulum suspended from a fixed point here. So this is a fixed point, and this is a pendulum which consists of a bob and a string. Then it is actually swinging from here to that point. The bob is slightly pulled to position A and then released. When it is pushed here, it is released, it will start swinging like that. Then they are saying state one factor that does not affect the period of the pendulum. So this period of the pendulum has been studied, and it has been found that there are things that does not affect the period of the pendulum. So what is the period of the pendulum? This is the time taken to make one complete oscillation. All right, the time taken to make one complete oscillation is what we call a time period. So one oscillation is when you pull this one here, you allow it to swing. Definitely it will come like this and then come back like this. So this will be one oscillation. When it goes and it comes back, it makes one oscillation. So now they are saying now that state one factor that does not affect the period of the pendulum. So it has been studied that the factors are: 1, mass of the bob. So the mass of the bob does not affect the period of the pendulum, the time it will take to go here and come back. Then another one, it is actually angular displacement. So this angular displacement, to some extent, it does not affect. So the correct answer with surety is mass of the bob does not affect the period of the pendulum. All right, so let's move to the next part. The next part B here says if the values of time for 20 oscillations obtained were, so we have 16.1 seconds, 15.9 seconds, 16.0 seconds, 16.2 seconds, and 15.8 seconds. Calculate the period of the pendulum. So let me make you understand, because this is quite tricky, but it's so simple at the same time. So why we have these many values here? The reason why we have these many values here, it is the desire to arrive at the correct value. So if someone did this, it means he did first oscillation, he got this one, he repeated the same, he said, let me do again, I see what I'll get. He repeated the same, then the time was this. Again he repeated, again it was this. Again he repeated, again it was again. So he got this. Now he wanted to do it many times so that he gets the accurate value. So since he corrected these times here, if they are saying calculate the period of the pendulum, before he calculates, he needs to know the average time these 20 oscillation took. So the average time, which I'm calling T average, must add all the time here, this plus that plus that plus that, then divided by the number of these 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So you divide by 5. Then you add. When you add, you divide by 5, you find that it will be 16.0 as the period, as the time. Now, period is calculated using this formula. Period is equal to time. Now you use average over number of swings, which is going to be time. You have already gotten 16 divided by number of swings, which is 20. When you divide, the answer will be 0.8 seconds. So C, calculate the frequency of the pendulum. So frequency is by definition, frequency is the number of complete oscillation made per second. Number of complete oscillation made per second is what we call frequency. But remember, time period, we said period of the pendulum, we said this is the time taken for one complete oscillation. But for the frequency, we are saying it is the number of oscillation per second, time taken for one complete oscillation. So they are opposites. So frequency and the time, they are opposite, or they are inverse. So that's why we say frequency is equal to 1 over a period. So this is the frequency is equal to 1 over period. It is inverse. So say it is equal to now 1 over period we already found, which is what? 0.8. So say 0.8. When you divide this one, you get 1.25 Hz. These are the units for frequency. So you put 1.25 Hz. Let's move to B2. B2 says a car has a mass of 900 kg. Then it accelerates from rest at a rate of 1.2 meters per second. So this is the acceleration. The car has a mass of that. Then they're saying calculate 1 time taken to reach a velocity of that. So here now they want velocity, guys. Oh, not velocity, time. So there's this velocity here, and then it started from rest. So we have acceleration, then we have what? This final velocity. Then they're asking us time. So we'll call the formula which connects these three. 1, 2, 3. Then we have also rest here. So same, it is this formula which says acceleration is equal to final velocity minus initial velocity over time. Then they want time. So make time the subject of the formula, which will be time is equal to now final velocity minus initial over acceleration. So time is going to be, final velocity is this 30 minus initial, since it started from rest, meaning rest means stationary. If something is stationary, it's not moving, it has 0 velocity. So 0 divided by acceleration is 1.2 meters per second square. So that would be that. So when you divide this You say 30 minus 0, 30. 30 divided by 1.2, it will be actually 25 seconds. So time is measured in seconds. So let's go to this question here. Then they're saying 2 force required to accelerate the car at a rate of 1.2 meters per second. So they want force. So you know force is equal to mass times acceleration. And here we are told the car had a mass of 900. So say force is equal to, where there is a mass, we'll put 900. Acceleration is 1.2. So m8 means mass times the acceleration. So mass 900 times acceleration 1.2. If we multiply this, we'll get 1018 Newton. So force is in a Newton. Don't forget the units. So you put that. Then let's go to another question. Question B3 says figure B3.1 below is a diagram showing a rod being moved using a wheelbarrow. So there's a rod here being moved using a wheelbarrow. So they are saying the total mass of the wheelbarrow and the load is 80 kg. So the mass of the wheelbarrow and the rod is 80 kg. Take G to be equal to, this G is acceleration due to gravity too. So they're saying take G equal to 10 Newton per kg. Then they're saying A, calculate 1, weight of the wheelbarrow and the rod and the load. Weight of the wheelbarrow and the load. So you need to know the formula for calculating weight. Weight is equal to mass times acceleration due to gravity. So mass, it should be mass of the object. Which object in equation? It is the load and the wheelbarrow. Then acceleration due to gravity, it is given 10. So mass is 80. So weight is equal to now 80 times acceleration due to gravity, which is 10. So when we multiply 80 times 10, which will be 800 Newton. So weight is 800 Newton. So let's move to another question 2, which is saying here they said what? Calculate the weight. So 2, they're saying calculate force F required to lift the wheelbarrow. So let's bring the wheelbarrow here. So they're asking us to calculate this force here. All right. So now before I do that, you should understand that there's a principle of moment working here. So if a person lifts this wheelbarrow, or in other words, what I'm saying, for this wheelbarrow to be moved by a person, the person must lift on the handle here and then start pushing. Not so. That is correct. So now if a person lifts the wheelbarrow and starts pushing, you'll find that the tire does not move here. On the tire, as he lifts, the tire stays the same. So meaning the tire which stays the same, but on this part rotates at this point. This point then becomes the pivot. The pivot is the turning point of an object. Like the door, it has the hinge. So the hinge of the door actually are the turning point of the door as you open. Even in this one, as you lift it, the turning point is here. Now notice that there's a force here that which is the lifting force. Then here there's also a force facing downward, which is the weight of the load and the wheelbarrow. So this one becomes an equilibrium problem, where now the force upward time from the force upward times its distance from the pivot, this one becomes the pivot, is the same as the weight acting downward times its distance from the pivot. So we are going to say force then times what? D1. So we'll call force then this distance here from the pivot to where the force is, we'll call it D1. Then it should be equal to then the weight, then it times D2, which is the distance of the weight from the pivot. d2 from here. Then we'll say equals F is, we don't know, D, it will be this distance 1.5 plus 0.5, which will be 2, then equals, then weight, we found it to be 800 previously, the weight here, then D times d2 from here to here 0.5, then when we multiply F times 2, it will be 2F equals this times this, which will be 400. To remain with F, we divide by 2 here, even here by 2, so that this and that cancel. F now is going to be 2 into 400, which will be 200 Newton. So F here will be 200 Newton. Then here they're saying state whether force F would increase or reduce when the handles of the wheelbarrow are made longer. So when you increase the handles here, then the force actually will decrease. All right, so the force will decrease. So we are saying the force would decrease, and the reason is simple. Distance is a force multiplier. So when you increase the distance, then meaning the force that you are going to apply, it will be small, but it will still be the same constant, because it will now be increased by increase in distance. That's why long spanners can open a very, very hard thing, because when a long handle is used, it is multiplying the force which is being applied than when you are using a short handle. So let's go to another question. This is question B4, which says figure B4.1 below is a diagram showing a stone of mass 20 kg that was pushed up a slope from Q to R. So in this diagram here, we are told that there's a stone of mass 2 kg that was pushed from R, from Q here, the ground, to R, up the slope, pushed up a slope. This is up the slope from Q to R. So the stone is there. Then they're saying 72 joules of work was done in moving the stone up the slope from Q to R. So the energy which was used here is 72 joules. To do what? The work which was done was 72 joules to move the stone from Q to R. Then A, what is the potential energy of the stone at R? All right, so they need what? Potential energy. So we know potential energy is equal to mass times gravity times height. Do we have height here from the ground to where the stone is? No. Do we have mass? Yes, 2 kg. Do we have gravity? Gravity is always 10 meters per second square, or 10 kilogram per Newton. So it is always non-gravity. But since we don't have height, is there any way we can answer this question? Yes. So remember, work is the transformation of energy. Work is the transformation of energy. That is work. So when you are doing work, you are transforming energy from one form to another. So if they used 72 joules of work in pushing this stone from here to here, so they were transforming energy. So the stone, when it is on the ground, it has no energy. When it is above the ground, it has energy we call potential energy. So the same work which has been done to move it up, it is the same energy it has gained. So the energy used to push it there, it's the same energy it has gained, because anything raised above the ground has got a potential energy. So this one now has potential energy, and the potential energy it has is the work done is equal to the work done in pushing it there. And then the work done is 72 joules. So meaning the potential energy will be 72 joules. Then let's go to another question. B, which says if the stone falls through side RT. So this stone now here, it falls through this side RT here, RT. What would its potential energy be at S, the midpoint of its fall? So when it starts falling, they're saying when it reaches S, which is the midpoint, from R to T, what will be the potential energy here? So simple, right? Because here we are saying potential energy at S is equal to half of the potential energy at R. So the potential energy at S should be, since it is on the middle, at R it is 72. Then when it has moved halfway, so 72 divided by 2. That's why we are saying that the potential energy at S is equal to half of the potential energy at R. So meaning potential energy is now going to be half times 72, which is going to give us 36. So we are halving this one, then we are getting 76 joules. Then C, calculate height RT. So they want us to calculate height TR. So simple. So we use potential energy is equal to mass times gravity times height. Then we need height, right? So height, make height the subject of the formula. You have height is equal to potential energy divided by mg. So potential energy at half distance now is going to be actually 36. So we are going to say equals then 36 here divided by mass is 2 kg. We are told 2 kg times 10 here, which is actually the acceleration due to gravity, so which will be 1.8. If you evaluate this, you get 1.8. Then they're saying velocity of the stone just before it strikes the ground. So the stone as it falls, its velocity before it hits the ground. So we know that velocity is equal to this formula here, square root of 2 times g times height, because it is falling. So when an object is falling, the shortest formula you can use to find its velocity is this one. Velocity is equal to square root of 2 then times gravity times height. So we are going to say is equal to, so here 2 times gravity, acceleration due to gravity 10, times height, which is 3.6. So here we are using the total height now. So instead of 1.8, now the stone we are counting as it moves from the top, the total height. So if you say 1.6 times 2, because this one was just RT, it was just RTR. Now we have considered from the top to the bottom. So if you say that, if you try to calculate this one here, if you try to calculate here, you find that if you say 1.8 times what? Times 2, to be 3.6, the whole height. So that's why we're saying 2 times gravity times height, 3.6, when evaluated to be 8.5 meters per second as the velocity. Then let's move to this question. B5 says figure B5.1 below is a diagram showing a wave traveling along a spring in the direction shown. So there's this diagram here showing a wave traveling along a spring in a direction shown. So this is the spring, and then a wave is moving like that. Then they're saying, in what way is this wave the same as a sound wave? Yeah, so when you look, it has this compression, these rarefactions, compression, rarefaction, compression. Because of this rarefaction and compression, meaning it is pushing like this, then it comes, it pushes like that, it comes. That's why it has compression and the rarefaction. So meaning that in what way now they're saying this wave is sound wave? So simple. It is because in the way that the parts of the string vibrate parallel to the direction of travel of the wave, which is similar to the vibration of particles in sound wave here. So we are saying the string, or the parts of the string, these ones vibrate parallel to the direction. So they vibrate like this. This is the wave direction, and then they vibrate parallel to the direction of the wave, and this is similar to the vibration of particles in sound wave. Then they are saying what are regions U and W. So this U is compression, and then these W are what we call rarefactions. So let's move to another part, B6. A ray of light travels from air into water at an angle of 40 degrees Celsius between the normal and the incident. So there's a ray of light, guys, traveling from what? From air into water at an angle of 60. So let me say here maybe we have a boundary, then here we have some water, then here we have air. So we have air this side, water. So we have a ray of light traveling from air. So it is traveling from air going like this. Then it is making an angle of 40 with the normal. The normal is a line which is at 90 degrees like this. So the angle here is 40. So this is the normal. Then when it reaches here, actually it refracts towards the normal like that. Because when a ray is moving from less dense media, air is less dense media, going into a more dense media, water, the ray will bend towards the normal. So they are telling us that its ray produces an angle of refraction of 29. So an angle of refraction which will mean here to have 29 here between the normal and this ray. Then they are saying we calculate the refractive index of water. So the refractive index given by this formula is going to be a sine angle of incidence divided by sine angle of refraction. So angle of incidence is this one, which will be 40. So say refractive index is equal to sine 40 over, then here sine refractive angle of refraction, which is 29. So 29. So when you punch on your calculator, what you should find is this. If you get sine 40, so let me just do like brackets. First let me cancel this one. Let me say brackets. So cancel brackets. So let me say 40. Then let me go to trigonometry, sine 40. Then I'll say cross brackets, then divided by again, then I'll say open brackets, then 29, I'll say 29, then again let me go to sine, then cross brackets and say equal to. So I've found what? 1.3. So 1.3 here, so the answer will be 1.3 as the refractive index, 1.3. All right. So now here they are saying the critical angle of water. So critical angle is given by sine inverse of 1 over angle of refractive index. So C critical angle is equal to sine, this one means inverse of 1 over refractive index. Refractive index is already 1.3. So now we'll just substitute here. So we are going to say critical angle is equal to sine inverse 1 divided by 1.3. So now what we are going to do here, maybe to help you to know how to punch, so you just say 1 divided by 1.3. What do you get? You get 0.769. Let's end here, 769. So that's we have gotten that. So now what we are going to say here, we'll use now the inverse. Do I have the inverse here? Seems I don't have the inverse on this calculator, or I don't know how to use the inverse. I don't know whether it is this one, but let me try. I don't know, but I know on these other calculators there's inverse, which looks like, or you press on shift on those calculators, that's when you get the inverse. So this one maybe it will be 0.796, I think. This is what I found. 1 divided by 1.3769. Okay, so I'll say 0.769. Then let me try this one here and say equals, no, this is not the one, so I don't know how to find the what. Is it this one? No, so this one actually I don't know how it moves. Maybe second. Oh yeah, like this one. Very good, I found it. So I'll say 0.769. then I'll come here, I'll say this one, then I'll say equals. No. Why am I getting this wrong answer? Let me put in advance, maybe second sine, let me say 0.769. Critical angles, yeah, we are saying okay, let me do like this. Let me say like this one, open brackets, let me say open brackets 1 divided by 1.3 close brackets. Then I say trigonometry here second, then I'll say sine, I think, yeah, then equals. No, that's not what I found. I found it to be 50 degrees, guys. 50 degrees as the answer. So try it and let me know what you find on your calculator. So let's move to this question 7. P7 says figure B7.1 is a diagram showing 240 volts main supply connected to a television set and 2 lamps. Yeah, so we have a diagram showing 240 main supply. So this is 240 AC supply connected to television. We have this one coming here connected to a television. So this is a live wire where there's even a switch connected to a television, and 2 lamps, and then 2 lamps here, 40 watts, this one 120 watts. Yeah, so these are in parallel like this. So these 2 lamps and the television, they are in parallel. Then they're saying the power supplied to each lamp and the television is 40 and 120 respectively when the switches are closed. And this switch is closed and this switch is closed. Here to receive 120 power, 120 watts. Here to receive here 40. Then they're saying calculate the one total power supplied. So power, you just add this one plus this one plus this one, which will be actually power is equal to this one plus this one 80 plus 120. When you add it, will be 2000 watts. So power is not the same in parallel, but it will be the same, I think, in series. But in parallel, it is not the same because remember, power is equal to current times what? Voltage. So in parallel here, voltage will be the same. These guys will have also 240 volts. Then these also will have 240 volts. However, what you should know, however, is that current, when it reaches the junction here, current which comes here is different. So here in this one, let's say there will be current 1, and in this one there will be current 2. So here there will be different current, and here different current. So when calculating current here, current, when current reaches a junction, it branches. Some current comes here, which we are calling current 1. Some current goes here, which is current 2. So they differ. So since current differs, so here there will be current what? 1, for instance. Then another power is going to be calculated as current 2 times the same voltage. So if here there's different current, meaning this different current times the same voltage, 240, it will give you another power. Again here, this different current here times the same voltage, 240, it will give you another power. So power, that's why it differs. That's why you need to add the one which is here and the one which is there, which will give you 200 watts. Watts are the units of power. Then B, we calculate what? Total number of kilowatt hours of energy supplied to the circuit in 3 hours. So they need now the total number of kilowatts hours of energy. So they need energy in kilowatts hour. So energy is measured in joules or in kilowatt hour. So energy is always equal to power times time, and the time must be in hours. So energy is equal to power, we have found to be 200 times time in hours here. So it will be 3 hours. So energy is going to be this times this, which will be 600 watts per hour, because this one is in watts, this one is in hour. So watts per hour. Now they want it to be in kilowatt hour. So since they want it in kilowatt, we need to divide by 1000 this one for it to go to kilo, because kilo stands for 1000. So when we divide by 1000 this one, it will be 0.06. Then we put K watts hour, kilowatts hour. So this and this, they are equal. Here where there's K, it's just that 1000, we have just put the units. Divide by 1000, then you get 0.6. You put K watts hour because we divided by 1000. So this one will be your answer. Then in 2, we calculate potential difference across the television set. So potential difference here, guys, I said it will be the same. These guys are in parallel. So potential difference across this television set and these are the same. Here we are being supplied with 240. So 240 is the same. So voltage is the same in parallel. So we have 240 here. Even here it will be 240, but they want potential difference across the television set here. So it will be 240. Then let's continue. So yeah, that is it, unless otherwise. Yeah, So unless otherwise. So now let's move. B8 says figure B8.1 is a diagram showing a coil of wire wound on a soft iron core with current flowing in the direction indicated by the arrows. So we have this diagram here showing a coil. So this is a coil of wire wound on a soft iron core. So this one is a soft iron core. Now they're saying with current flowing. So there will be current flowing in those direction of arrows. All right. Then they're saying mark the N and S poles induced on the coil. So we mark the N, the north and the south poles induced on the coil. So now here we are going to use the right hand grip. So this is the right hand grip for us to mark which one will be south and which one will be north on these two ends of this iron core. So we use this right hand grip rule. So the right hand grip, when the fingers are coiled in the direction of current, so you see how it is coiling these fingers facing that way in the direction of this current, because current is going like that. So even here it will be like that everywhere here. All right. So if this hand is brought here to face that way, then this way it will be north, then this way south. So this way north, like you have seen north, then this way it will be south because of that. So meaning we are saying this way it will be north, this way it will be south. So mark the N and S poles induced on the iron core. We have marked N this side, south. All right. So now question B says show by an arrow the direction in which a plotting compass needle would point when placed at point X. So we have these 2 points, X and Y. So if you get a compass, you place it at point X. In which direction the arrow of the compass will face? That's why they are saying show by an arrow the direction in which a plotting compass needle would point when placed at point X. So you know a compass needle, a compass has got a needle which points in directions. So it is like that. But what you should remember, that this pointer here, like this, it is north. Then the tail this side, it is south. So if this one is a compass like this, if you brought a compass at point this one, so if this one is south, this one, then if you brought it here, it will face this way. The pointer will face this way, where there is a south, because this north of the pointer and the south, they will attract each other. So it will face this way. Why? Because that's where the direction move. So this is how this actually produces the magnetic field. They'll go like that. So now the magnetic field moves from north to south. So that's how it will point. It will point that way. The way these are pointing that way, even the pointer here, that's how it will point, entering like that. All right. So let's answer another question. So I've put like that. So C is saying a beam of electrons flows through point Y in a direction perpendicularly downwards into the page. Then they're saying show clearly using an arrow labeled F the direction of the force exerted by the magnetic field on the beam, on the electron beam. So quite tricky. So they're saying there's a beam of electrons. A beam of electrons flows through point Y in a direction perpendicularly downwards into the page. So there will be some beam of electrons moving from up the page, going into the page, like that is a beam of electrons going there, entering like the page, moving from above this page where you are looking above, then entering. I can't show it here, it's hard. So entering there into the page. All right, so then they're saying if that is the beam of electron doing like that, going like that, then they're saying show clearly using an arrow labeled F the direction of the force exerted by the magnetic field on the electron beam. So what will be the direction of the force on the electron beam? So here, for us to answer this one, we need to use what we call the right hand rule. Fleming's right hand rule. So this is Fleming's right hand rule, where when you hold your fingers, your thumb, your first finger and your second finger at right angle like this, so the angle between this finger and this one, they're making 90 degrees, and then the angle between this finger and this finger here, there's 90 degrees, and also this angle, this finger and this finger, they're making a 90 degrees there. So there's 90, 90, 90. If you hold them like that, then this finger here will show most direction of movement of whatever something that is put in the magnetic field, then it will move in that way. Then this finger here, in that direction, it points in the direction of field. Then this finger like this, it points in the direction of current. So if you, this is current, right, which will be actually the beam of electrons will move in that way. So now the issue is this. So if you are to come and get this finger, this hand, place it here so that it obeys this statement here. A beam of electrons flows through point Y. So this is beam of electrons. So if you were to fold in a reality, this hand you rotate it. So this hand must rotate until this points like into the page. So if you rotate this one, it goes like, it will point like that into the page. You rotate this one, it points into the page. You'll find that this thumb here, when you rotate like that, when you rotate like that until this one faces into the page, like beam of electron flows perpendicular downwards into the page, then this one will face downwards. This finger will face downwards, right? However, there's an opposite way I didn't realize. So what you should know is that the direction of current, guys, this is the direction of current, is opposite to the direction of the beam of electron. Yeah, that is one thing again I didn't realize, I didn't apply there. So the direction of the beam of electrons, if electrons are going into the page like this, entering into the page, then current must be coming out like this. That's how it is. So yeah, so if current is coming out like this, then it means electrons are going like this, pointing into the page. Then this finger points into the direction of magnetic field. So if you shift the whole of this part here, you bring it here the way it is, because this one will mean current is going, a beam of electrons is going like that. It's tricky, guys, that's why I'm taking long. So there's this one going like that, which is the beam of electrons entering into the page like that, but this finger is pointing in the direction of current. Now remember, this is the south, so meaning the fields are going like that. So this one which is pointing in the field is going like that. So meaning field will point like that. Then there's this finger here pointing upward. So this finger is pointing upward. So this finger means motion. So when they say now show clearly using an arrow labeled F. So it will be like this. That's when I've realized the first answer I gave was wrong. I gave the one which was facing downward. But now I've remembered this principle very well. And in the other video, I answered upward. But when I was revising today before recording, I thought I had made a mistake. But then I've realized I was correct. So, because if field is facing like this, current, then electron should be in that opposite direction to the direction of current. So then this one is in the same, is in line. So this one pointing in the direction of the field, north to south. So this is south, it is going like that. So when you shift this one or bring it here, you find that these fields are going into the page. Yeah, they're going into the page, because current, if it is going like that, then current electrons goes like that. So when you push it like that, electrons will be going like that, like that, like that. Then it will move upwards. So that will be the answer, guys. So this answer of mine here, it is wrong. This one is wrong. The correct one is like this, like I answered it previously. So this one is F. That's the answer here. So now let's move to another question. Question B9. Phosphorus 32, which is they're saying phosphorus 32, which is the symbol is P32, can decay by emitting beta particle. So it can decay by emitting beta particle. We have done this in radioactivity. If you want to join radioactivity, the number is on the screen or in the comment, I mean in the description section. You can join my WhatsApp group where you can learn extensive extra lessons on radioactivity. We are remaining with one party where I have to teach only half-life and then the uses of radioactive substances and then precautions. That's all, then we are done. So if you want to learn radioactivity, join through the number in the description or you'll find it on the screen. So now, what now they're saying is phosphorus 32, meaning the mass number of phosphorus is 32 here, guys. Now, which is the symbol is P32, can decay by emitting beta particles. Then they are saying, what is a beta particle? A beta particle is just a fast moving electron. It is a fast moving electron. That is a beta particle. Then they're saying, if the proton number of phosphorus 32 is 15, state the new values of proton and mass numbers of the nuclide just after it emits a beta particle. So this one, phosphorus in P32 here, as the what? As the sorry, not that one. This one is wrong. Let me put it here. So P, phosphorus P, then 32 must be here, the mass number. Then it has, what is this one? Proton number, they're saying is 15, which is atomic number. So when it decays, it breaks. They're saying decays by emitting beta. So if it decays by emitting beta, it will form a new element plus a beta particle is just 0. Then E, it is an electron with negative 1 here. Here 0. So now, beta particle, what happens in beta particle? What happens in beta particle is that a neutron breaks. A neutron here breaks into a proton and the electron. This is the electron which comes out. So a neutron, when it breaks, it changes into a proton. So now here, if it changes into a proton, meaning if you have 15 proton on this guy, it will be 16. Yeah, 16. Then this guy here will remain the same, 32, because a neutron, when it breaks into an electron, this number should decrease by 1. Now that a neutron, when it breaks into an electron comes out now also into a proton comes and adds itself here. So here in 32, for instance, let me just make this thing clear here. So in 32 here, if there are 15 protons, there are neutrons here there. So you say 32, sorry, there's something. 32 minus 15 equals, which will be equals 17. So there are 17 neutrons here. So number of neutron is actually what? 17. Number of protons is actually 15. So 15 plus 17, it gives you this mass number. Now this one neutron here breaks. When it breaks, to undergo beta particle decay by beta, it breaks to give you this electron here, electron or -1 here. Where are we? It's tricky, quite tricky, guys. So it breaks to give you an electron, -1, 0 of 0 mass. Then, and also what? A proton plus a proton here. All right. So plus 1 proton, meaning here when one neutron breaks, it will remain what? 16. Now a proton has been formed. So that one proton which has been formed, one proton comes and adds to these protons, so that you have now plus 1, so that now you have 16. That's why this guy will have 16, the new element. Now if you say 15 plus 1, 16. 16 again plus 16 goes back to 32. That's why here it remains 32, 32, 32. Here now it will be 15, 16. So that's why it is. So when they are saying that state the new values of proton and the mass number, so the proton will be 16, the mass number will be still 32. So this is what I answered. I thought I should explain for you to understand. So this is the decay equation which I've explained. If you have this phosphorus here, when it decays by beta to give a new element, the proton number increases by 1 because a neutron breaks to go into an electron and a proton. Then the mass number here remains the same. So if it remains the same, so if you have 32 here, 32 here, even here 32. If you have 15 here 15 plus 1, 16. That's why we are saying here proton number 16, then mass number still 32. Then they are saying write the decay equation for P32 after emitting 2 beta particle. Now instead of emitting this one, now it emits how many? 2 of them. So if it emits 12 of them, the decay will be this one. This one now decays to this one 17. Now here it will be 17 because one decay gets it to 16, another decay gets it to what? To 32. Then plus now there will be 2 electrons or 2 beta particles which will be emitted because it has emitted 2 of them. So you put 2 of them there. So this is how it is going to be. Now see, phosphorus 32 can be used to prove that plants absorb phosphorus nutrients from the soil around them. So state 1, safety precaution which should be taken into consideration when doing experiments with phosphorus 32. So these are just precautions, guys, that must be taken when someone is handling a radioactive substance. So what precaution do you take? We are saying wear radioactive protective gear. This is one answer here. They asked for one, but I had to put all of them. So the one safety precaution is wear radioactive safety gear. 2, avoid consumption of the radioactive sample. Don't consume it. Then 3, avoid spillage of radioactive sample in the environment, so don't spill it. Then 4, dispose of any unwanted sample in allocated areas. So these are 4 of them. Here they only needed 1, so the best one is this one here, wear radioactive protective gear. All right, let's go to question C. Now we are done with the B. Let's go to C. So C, we are told that you're answering it. We are answering O. C1 is saying figure C 1.1 below is a velocity time graph representing motion of a motor cycle traveling along a straight road. So this is the graph here. This is the motion of a motorcycle traveling along a straight road. All right, so let me interpret this one for you. So when you look at this graph, is the same as this one. So from O to P is the same as A to B. So here AB, since if here AB represents constant acceleration, because if you have velocity time, then this line which goes like this represents constant acceleration. Then this line here represents constant velocity or speed. Then this line here represents constant deceleration or retardation. So here constant acceleration, here constant speed, here constant retardation. So I thought I should explain this before we start answering the question. All right, so then they're saying describe the motion of the motorcycle between the points Q, O, and P. So here O and P, the motion of the car is constant acceleration. Then here it is P and Q, it is constant velocity. Then Q and R, it is constant deceleration or retardation. So this is what I answered. This one, constant acceleration, or P, this one, or P, constant acceleration. Then this one, constant velocity, this one, constant velocity, P, Q. Then this one is actually constant deceleration or retardation, which is this one. All right, then here they're saying what is the maximum speed of the motor cycle. So the maximum speed is found as a 60. It's a 60. All right, so here the maximum 40, I mean. So when the motorcycle started from rest, it accelerated. So when it accelerated, it reached 40. This is where you read velocity in meters per second, which is speed here. It reached this point, then it started going horizontal like that, meaning this is the maximum speed, which is 40. That's why I said 40. Then how long did it take the motorcycle to retard to rest? So how long did it take for it to retard to rest? So we'll come to it. So now in my answering, I think I had made a mistake. Again, even in the revision, I didn't consider that. So how long did it take to retard to rest? You consider from here. So from here, it started retarding to rest. So when they say how long did it take the motorcycle to retard to rest, you count from here to here. So from here up to there. So here you check that this is the middle. If this is a 6, this is a 5, and this is what 12. So you say where are we here? So you say 12 minus 5, what do you get? 7. So from here to there it is 7 because this is when it retarded. Yeah, so here you are going to say 7, not what I said. So it will be 7 seconds, guys. All right. 7, I said 7 seconds, not this one. What do I want? Oh, yeah, it's fine. Then they say calculate the total distance traveled by the motor cycle. All right, the total distance is the area under the curve. So we'll say total distance is equal to area under the curve. And when you look at that curve, it is a trapezium because it has gone like this, like this, like this, like this. So that kind of an area, a shape it has formed, it is a trapezium, guys. So now, since it is a trapezium, this is the formula. So it's equal to trapezium formula. Area of a trapezium is half, then open brackets a plus b, close brackets times h. So we'll say equals, then if you check properly, you'll find that this 1 over 2 here, then we'll come and find what a is and what b is. So a and b are the parallel sides of the trapezium. So when we come here, this is the trapezium shape. So the parallel sides are these. So from here to here, it is actually 12 because there's 12 here. And also from here to here, it's actually 4 because here, if it is in, I think this should be 7 or so, right? 7, I think. Yeah, what did I answer previously on that other question? I said 12, right? Minus what? 5. That's what I said. Okay. Now, it was from here. Let me see, guys. It's like I might have lied backward here. From here to there. Sorry, guys. This one was a lie. The first one. So, from here to there. So, this one is actually 5. This is a 7 here. 6, 7 on the middle. Yeah, so I've realized. So from here, sorry guys, to there, it's not a straight line. How can I draw a straight line? Where can I find drawing for straight line? Any problem? These guys, they don't provide drawings for straight lines here. So yeah, just that. So from here to here is what they wanted the time, guys. Yeah, so you are saying 12 minus 7 here. So the opposite, 12 minus 7, which is actually 5. So here I should have said, instead of this one, 5 seconds. Thank you. Yeah. This one. Oh, not that one. So this one here where I said 12, but not 12, but 5 seconds. Then calculate the distance traveled by the motor cycle, where I said the distance will be equal to the area, total distance area under the curve, which said the formula of a trapezium, a plus b times h. And I said this one, a plus b. Then I said when we come here, then we realize from here to here, where we are going to say a is from here. So when you come here, it should have been, this should have been 6. So you say 7 minus from here, which will be 2, 3. So 7 minus 3 to be 4, yeah, A4. So from here to here it's 4. Then from here to here it's 12. There's 12 here. So we have known B is 12, A is 4. So you come, you say open brackets, A4 plus B12, close brackets. This one H is height from here to here. It is from here 0 to there, which is 40. Yeah, so like that. Then you evaluate, you'll find that the answer will be 320. So it will be 320, guys, when you evaluate this. This is mathematics, no longer physics. Then secondary, now we need to find what? The speed. Here I never brought back, so let me bring back the other question. Sorry. So the other question that we need to find is this one. Calculate the average velocity for the whole journey. So after finding this one, we need now the velocity. Velocity is equal to average velocity, VA, average velocity, but you can also do like this, a bar there. So average velocity is equal to total distance over total time taken. So you say total distance is this one, 320, total time is 12 there. It was 12 from here to here, it is 12. You can see 12 here. So meaning you put 12 there, which will be equal to 26.7 meters per second as the total average velocity. All right, so yeah, that is 12. If the maximum was 40, then the total average velocity was actually 12. Yeah, it makes sense. Then let's go to 2. 2 says a learner carried out a Hooke's law experiment and obtained the following results. So these are the results: mass in a kilogram, 0. Then the length of the loaded spring when he never added the mass. This pupil, when he or she never added the mass, the spring was at 11. When added the 0.02, the spring now stretched to 12.1. When added another mass of 0.04, the spring stretched from 11 to 13.2. When added 0.06, a spring stretched from 11 to 14.3. When added a mass of 0.08, a spring stretched from 11 to 15.4. When added a mass of 0.10, a spring stretched from 11 to 16.5. Then they are saying, let's see here, A, copy and complete table C2.1 by finding values of applied force and extension in millimeter produced. So we need now force here. So if there was no mass here, then the force should be 0, guys. Now, if the mass was 0.02 kg, then what will be force? Force is weight. Force is weight. So weight is equal to mass times acceleration due to gravity. So acceleration due to gravity is always 10. So if we get like this one, you say 0.02 times 10, it will give you what? 0.2. So that will be the weight. So here 0.2. Also here multiplied by 10, 0.4, by 10, 0.6, by 10, 0.8, by 10, 1. Then extension now. So extension, when you haven't loaded anything, the spring will not extend. So it will be at 0, guys. Now when you have added this one, or a force of 0.2 or mass of that, then it goes from 11 to 12.1. So then for you to find extension, final minus original. So you just say, okay, you get your calculator there, you say, let me move it, you say final 12.1 minus 11. What do you get? 1.1. So here it will be 1.1. Then here again, final minus original, which will be 13.2 minus 11, which will be 2.2. Again here you say 14.3 minus 11, which will be 3.3 continuously. Then here you say 15.4 minus 15.4 minus 11, which will be 4.4. Again you say 16.5 minus 11, which would be 5.5. So these are the values which are going to be here: 1.1, 2.2, 3.3, 4.4, 5.5. So we are done with this one. Then B, plot a graph of applied force N against extension mm. So this is where most of you have a problem in plotting the graph. So simple. So let's see how we can plot this one. So let's get the values we are plotting. Applied force, which is this one here, against the extension. So this one, applied force, always vertical axis, then extension to be horizontal axis. So when we move here, we get our values, our table, applied force here, extension here, we get our graph like that. So when we have our graph here, what we should know is that on the horizontal here we have extension, then on the vertical we put force. And make sure this graph should have a name. Here it should be force against extension. All right, then here you always have origin 0, 0, 0, 0 here. Now you need to look at what we call the scale. However, the scale must be the fact that the values that you plot here must suit. So here, when you look at force applied, you are beginning from 0 up to 1. So meaning the values that must be put here must fall within these. So it is simple. So you look at their uniform. There's 0.2, 0.4, 0.6, 0.8, 1. The difference from 0 to 2 is actually, 0 to 0.2 is actually 0.2 itself. Again, the difference from 0.2 to 0.4, it is 0.2. From 0.4 to 0.6 is still 0.2, 0.2. So this one is a no-brainer, so simple. However, this one again, you see there's 1, 2, 3, 4, 5. So these one are just point, which are these small lines. These are points here, these are small lines. So meaning 1, 2, 3, 4, 5. Just put that 1 here, 2 here, 3 here. So make sure 1 point here. So if this is 0, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, 1. So you make these 10 of them. Yeah, because we are given a big graph. That's how it should be. So you give them like that. So here we have up to 5.5. So say 4, 5. You can even end like that. If you want, you can even put 6 here. Then from there now, what we are going to do now is to go this way again. So this way, since it is a difference of 2, 2, 2, 2, 2, you can even say that from here to here, give it 0.2. From here to here, 0.2 plus 0.2, 0.5. All right, then 0.4. 0.2 plus 0.2 to to give you 0.4. 0.4 plus 0.2 still, it will give you 0.6. 0.6 plus 0.2, 0.8. 0.8 plus 0.2, it will give you 1. So it has scattered from 0 to 1. So they are equal in distance, from here equal, from here equal, from here equal, from here equal, from there equal. Now you have done that. This is the most important thing. After that, now you start plotting 0, 0 here. You start with this one, 0, 0 here at this point. Then from there you have 1.1. So this is 1. This is 1.1, 1.2, 1.3, 1.4, 1.5, 1.6, 1.7, 1.8, 1.92. But you are ending at 1.1. So this is 1.1, comma what? 0.2. So 1.1 is here. You move until you reach this line 0.2, somewhere here. You make a pointer there. Then again you go 2.2 is here. 2.1, 2.1, 2.2, comma what? 0.4. So you go to 0.4 somewhere here. You put a point. Then here 3.3. 3 is here. 3.1, 3.2, 3.3, comma what? 0.6. So you move up to 0.6 somewhere here. Then also 4.4 somewhere here, comma 0.8. You move 0.8 where? There. Then 5.5 is here, comma 1. You move up to where? There. Then what you do now, you draw a line. You'll see that this one will be a straight line like that. All right? So you have done. So here I didn't write. So you are supposed to say force here. Give it a name, force versus extension. Give it a title. A title is important. A title. Then the axis, you label them like that. Then you draw. There's nothing where you say scale. There are some people that lie to you that put a scale to say maybe if from here to here it is 1 centimeter, then you say 1 centimeter is equal to how many units here? 0.2. That is y-axis. Then on the x-axis you say from here to here, if it is 1 centimeter, you say 1 centimeter is equal to 1 unit. Here 0.2 unit, here you say 1 unit. You say this is x. These, they don't matter. They don't matter. The examiner is mature enough. What matters is these things are uniform throughout. You are producing values. These, if they are uniform throughout, if your graph does not follow my values like that and like that, it follows other values, no matter how different they are going to be. When calculating anything using this graph, it is going to be equal because the line is constant. That's how it is going to be. So these really don't matter. What matters, you put the title, this thing, you put your numbers properly, you put the points, you draw properly. That is all. What is it matters. These here, they don't matter. These ones here, they don't matter. All right, they don't matter. If there's such a rule, it's just wasting the students' energy and the time to answer. What has mattered is this. So now from there, let's see another question. So another question, I missed it. Let's see. Another question here must be saying, I never brought it. Say from the graph determine the spring constant. So let's see from this graph here which we have drawn. Now we determine the spring constant. So the spring constant is the gradient of this graph. Excuse me. So we can pick any 2 points on this graph here to find the gradient. So we are going to say that spring constant is calculated from the gradient of the graph. So the gradient K spring constant is equal to any 2 points y1, y2 minus y1 over x2 minus x1 here. Don't worry, I had to put x2, but x1, which will be equal to, you come here, I picked this point, 2 points, and here 2 points. This one here, it will be y1, and then y2. So this point here can be y, not that one. So this one, yeah, this one, yeah. So this one, this other side, y2, this other point here, y1. Then this other one here, x2, there's a comma here, so 5.5 x2, 1.0 y1. I picked this point here. When you come here, 1.0 on the y. When you come here, 5.5. Then I picked again this one. This one, when I come here on the x-axis, 1.1 here. When I go there, 0.2 there. So those are the 2 points which I picked. All right. Then from there now, what now I did was this, guys. So is to substitute these now. So you come here, you put y1 was 1, y2 was 1, y1 was 0.2 over x2 was actually x2 was 5.5, then x1 was 1.1. So 5.5 minus 1.1, then you have, when you evaluate, the answer is 0.2 as your spring constant. So spring constant, I never put the units here. I made an error. It should be force over, then you put the millimeters here, but this is not really a good one because it should be in meters, Newton per meter. So you change this one into meters. So no, it will be the same. So it will be actually now here, just remove this one, it will qualify like that. So it will be 0.2 Newton meter. That will be the units. Yeah. So now D here says 1. Did the spring reach its elastic limit? The answer is no. The answer is no. And then the reason, they're asking for a reason. Explain your answer in D1. So if we say no here, then the answer is that because the graph was a straight line, which meant that the spring constant was the same. Yeah, so if the graph is a straight line like this, it means the spring has not reached its limit, because that's why I've put this answer. For a spring to reach limit, it must maybe bend like this. Then it reaches its limit like from 0 to A. That's where the elastic limit is. But when it goes beyond there, it has gone beyond. But that one did not reach because the spring constant is the same, or because it is a straight line. All right. Then last question, figure C 3.1 is a chart showing some components of the electromagnetic spectrum. So we have some components, blue, green, microwaves. Then they're saying use the list below to copy and complete the electromagnetic spectrum chart, where we have radio waves, X-rays, ultraviolet, gamma rays, infrared, and red light. Then state two properties common to all members of the electromagnetic spectrum. Then P, name a component of the spectrum that 1 has the longest wavelength, 2 is emitted by hot bodies. Then C, microwaves have a frequency of 10 to the power 10 Hz and velocity of 3 times 10 to the power 8 meters per second. Then A, calculate the wavelength of microwaves. 2, state 2 practical uses of microwaves. All right, let's start with this one here. So they want us to use the list below to copy and complete the electromagnetic spectrum we put here. So guys, there's a short way we memorize these electromagnetic waves. There are actually 7. We say roast, maize is very unusual, X mass gift. So roast, which is the radio, maize. So if microwave is this side, then we are starting like this. So roast, which is radio, maize, microwaves, is infrared, unusual, ultra, Christmas or Xmas, is very, very, which is visible here, unusual, ultraviolet, X-ray, gift, gamma ray. Now notice that here we have been given radio waves, X-rays, ultraviolet, radio waves, X-rays, ultraviolet, gamma rays, infrared, and red light. We haven't been given ultraviolet, I mean light, visible light. Light is made of these colors, so it means one of these guys is occupying these. So when answering, I said this one should be radio waves, microwaves, so roast, radio, maize, micro. So roast maize is, which is infrared, then is very visible, but visible light here. So visible light, we are going to replace it with red. So there will be red, green, and blue. These 3 here, they will represent visible light. Then is very, then unusual, which will be ultra. This one here will be here. So it's very unusual, X mass, X, which will be X-ray here. Then gift, then gamma ray here. So roast maize is very unusual, X mass, gift. Yeah, so that's what I did. So I copied that one, and when I said A, I got this one and put this one, roast maize. So here red, ultraviolet, X mass, gamma ray. Then 2, they said state 2 properties common to all members of the electromagnetic spectrum. So these they want 2, but they were many. I gave this 1, they are all transverse waves. So these are all transverse waves, that is one of them. Then 2, they all travel at the speed of 3 times 10 to power 3 meters per second in vacuum. So they all travel at the same speed in vacuum, in short. Then they all travel in vacuum. Yeah, so they travel at the same speed and also travel in vacuum, excuse me. And then the wave equation applies to all of them. Then they transfer energy. So they needed 2. You could put this one and this one, then that's all. But I put everything so that you understand. Then let's move to B. B, they are saying B1 radio waves. B1 was name components of the spectrum that one has the longest wavelength. So the longest wavelength is radio waves, which was here. Then is emitted by hot objects. Is actually infrared, emitted by hot objects. So longest wavelength is this side. So it is opposite. So if this one is longest wavelength, then the shortest wavelength is here. So, and where there's shortest wavelength, that's where there's highest frequency. Here highest frequency, here lowest frequency. So longest wavelength, lowest frequency. Shortest wavelength, highest frequency. Yeah, I just wanted to explain that. Then yeah, I've said radio waves, infrared. Then they're saying, let me check again. Then here, see, microwaves have a frequency of 10 to power 10 Hz and the velocity of 3.5 3 times 10 to power 8. I don't know why I'm saying 3 point. So 3 times 10 to power 8 meters per second. They are saying, hey, calculate the wavelength of microwave. So we have 10 to 10, 3 times 10 to power 8. So they want us to calculate the wavelength. So use this equation here. So velocity is equal to wavelength times frequency. So they want this wavelength. So the formula for wavelength now it will be velocity divided by frequency. Then we'll get velocity. We were told it is 3 times 10 to the power 8. Then frequency we were told 10 to power 10. Then when you divide, you find that it is 0.3 meters. 0.03 meters as the wavelength. Then the other question was that state 2 practical uses of microwaves. So one, there are many. One, micro oven. So they are used in micro oven, these microwaves. Then 2, in radar, which is actually communication. Then in also telecommunication. So radar in airports. Then telecommunication as well, like we communicate on phones. So they use these microwaves. So microwave oven, radar, telecommunication. So guys, we have come to the end of this revision. I hope this one now is fine than the other one. So guys, again, remember we are doing revision to make you pass science and pass it for good. Pass it for good. Where you want value, you want revision, so that when you go in the exam you do well. Let's do revision. I stated the price: 30 kwacha physics, 30 kwacha chemistry, meaning paper 1 you pay 30 kwacha the whole of July. Then paper 2 you pay 30 kwacha the whole of July. The papers we are going to revise: 2014, 2015, 2016, 2017, 2018. So these are the papers we are going to revise. By the time we'll be finishing, then I'm sure you'll be able to get through the exam with flying colors. All right, so if you are new to this channel, you haven't subscribed, remember to subscribe for updates. Some of you, when I post new videos, you don't see them because you have not subscribed. So subscription is a way of sticking around to the channel so that you receive updates. All right, so thank you for watching this video. The number on the screen, if you want online revision, just text me. If you don't want them, just stay as you are. Just use my videos, maybe they'll help you. Of course they'll help you, but if you want to do very, very well, let's be in the revision. As for now, bye and see you in the next lesson. Peace.